Hello wind energy students, Dr. John Schrage here, and I want to continue our discussions of the stuff in chapter 5 of your textbook that are about features that can modify the local flow. And this lecture is about the pages that are about obstacles to the flow. And you know, if you remember from the last lecture, this idea of obstacles and roughness can get kind of tangled up. And we talked about how roughness is kind of more like a texture to the flow. It's about a texture to the surface, rather. It, strictly speaking, is only defined in terms of like the features that are continuous and uniform for infinite extent in all directions and so on. But we're going to kind of see that in more detail here. And to kind of put it into kind of a little bit of a little bit interesting or novel of a context here, I want to think about it as if like maybe we have to come up with some sort of analysis of the wind around this fascinating tower built in Dubai. Of course, if you make something like that, it's going to be in Dubai. This is actually off of a little island just off of the coast of the city of Dubai. And I don't know if you're familiar with this particular famous building, but this is the Burj Al Arab. It looks like a beautiful building, kind of shaped like a little bit like a sail or something. And it looks like it would be a lovely, charming little building with like, I don't know, 15 floors or something like that. But that's just kind of the weird way the architect made it. The thing has 56 floors. It's over 1,000 feet tall. It's within a couple hundred feet of the what used to be called the Sears Tower in Chicago. This thing's huge. Okay, those aren't bushes and stuff around the edge of the tree. Those are building. Those are trees. This is a huge building. And it is built on an artificial island. Well, I'm not entirely sure the island is artificial. The causeway out to the island, anyway, is artificial. Just offshore from Dubai. It's surrounded by waters of the Persian Gulf all around it, and so on. And it's this 1,000-foot tall tower just stuck up there. What a brilliant example of an obstacle to the flow. Let's think about what this would mean for the aerodynamic roughness length. I mean, Z0, aerodynamic roughness length, is getting to be an old friend at this point. We've been using him for lots of purposes all along the way, and we know that the aerodynamic roughness length should be something related to 1/30th of the height of mean obstacles to the flow in the area. Recognizing that in the area can become a very difficult thing to define, but let's think about our obstacles. Well, I see some obstacles to the flow. Winds near the surface are going to have to be adapting to the low-level friction associated with, oh, I see a wave right there, I see some waves right there. I could probably actually study this from an oceanographic point of view and start coming up with like what are typical wave heights at this location in the Persian Gulf. And that's a lovely, oh look, there's a causeway out to this little island. That probably has some aerodynamic roughness length some mean height associated with it. I better take that into account if I'm thinking about the wind in this area. And oh yeah, the skyscraper. Okay, and we've got this 1,000-foot tall tower in the way. What does that tell us about the aerodynamic roughness length? I mean, does that mean that our value of Z0 is huge here? Because, I mean, if we're going to have the average value of the height of these objects that are in the way of the flow, well, one of them is huge. I mean, we probably have like a few feet high waves, the causeway seems to be about 10, 20 feet tall or something, and then a 1,000-foot tall thing. Apparently this is a very rough surface, right? Well, no. I mean, that's actually not what's going on here. It helps us illustrate that there's a big difference between what we mean by roughness and what we mean by an obstacle to the flow. And I recognize that we've been sloppy about that term. In fact, we even keep using this idea that aerodynamic roughness length is equal to 1/30th of the mean height of obstacles to the flow. I recognize that there's a contradiction there. Okay, we'll get that sorted out. I mean, roughness of the surface is about a very large number of small impediments to the flow. Impediment here is not a technical word, by the way. I literally just typed out the word obstacle to the flow and then disliked it. Literally just hit F7 in PowerPoint and it suggested as a synonym impediment. Okay? And let's use the word impediment to the flow rather than obstacle to the flow when we're talking about roughness. So like waves on the ocean are an impediment to the flow. Or the corn plants in a cornfield, they're impeding the flow. They are an impediment to the flow. But there's a more or less infinite number of them. They extend in all directions uniformly. The flow, as it blows over the cornfield, is not adapting to each individual corn plant. It's adapting to the fact that collectively the corn is exerting friction on that whole lower layer of the atmosphere. Okay? It is not a single impediment to the flow. It's an infinite extent of impediments to the flow with similar characteristics. That's very much in contrast to what this obstacle is. There's a single obstacle here at the surface, to use the terminology that comes from your book, with a very different scale. I mean, this obstacle to the flow, namely Burj Al Arab, is literally orders of magnitude bigger in this case, although it wouldn't have necessarily had to be that much bigger. It tends to be fairly isolated with more uniform areas of the surface around it, and the flow has to adapt to this feature. I mean, the flow is going to have to go around or over or whatever, all kinds of things that are hard to illustrate in PowerPoint. But you need to understand there's going to have to be some kind of flow going around it. It might seem like this idea of roughness and obstacles is just sort of academic gimcrackery, okay? The kind of thing that only pedantic scholars care about. But this distinction is not entirely arbitrary. It has to do with how fast air parcels can actually adapt to the underlying surface as they move over it. You're getting way into theoretical meteorology when you're getting into that, though. Thinking of this idea of roughness being about the texture of the surface and obstacles as being objects on the surface that the flow has to adapt to individually is probably your best bet to keep this sorted out at a very practical level. Now, there's a number of ways we could work to understand the flow around this model, around this obstacle here. The modern, awesome, cool way to do it would be with a full-blown numerical computational fluid dynamics model, where you're literally solving, you're dividing the area up around the building into millions and millions of little pixels and simulating the flow through each of them based on the 7 primitive equations, and we're going to see some examples of that. And that's really cool. And you can really see all the cool features as the flow separates, as it goes over the building and things like that, and we'll see some examples of that in just a little bit. But that's a lot of work. And it's hard to argue how that actually helps understanding from like a wind power perspective. Because while it might be really beautiful and interesting to watch these YouTube videos of flow swirling and forming little separation bubbles, to use terminology from earlier in this module and so on, what is that really telling you about the wind power? Basically all you want to know is, on average, how windy it is near your obstacle here. That's all you really need. You don't really need to watch beautiful little separation bubbles come off the tops of the building and so on. So we're going to be using an approximation to the flow going over an obstacle, but in fairness, I do want you to see some of these very cool animations that I found on YouTube of full computational fluid dynamics models illustrating the flow going over and around buildings in an urban setting and so on. I mean, they are literally just applying the basic laws of physics to air parcels and tracing them as they go over the building and keeping track of their velocity and their pressure and all these kinds of things. It's hard to keep this synced up with the YouTube video. You might be seeing the ones where they're carrying traces of pollution from a smokestack over the buildings. It's all really cool. But from a wind power perspective, it's not quite clear that gives us the information we really need anyway. But we don't just need to know the wind speed in like that little eddy. We really want to know what would we expect if we built something there and left it there for 30 years, right? What is the mean wind how is this thing going to affect the mean wind? Turns out in order to do this, we need to have a way of describing the area around the obstacle. We need like a coordinate system around our obstacle. And this turns out to be best done using a technique that atmospheric science people use all the time called scaling. We're going to use the height of our obstacle, so like the height of this tower in this case is, let's say, h meters, as like our new yardstick, our new unit of distance for both horizontally and vertically. So, we rather than saying this is what the wind is doing 200 meters up, and this is what the wind is doing 400 meters up, we'll talk about it in terms of like that's what the wind is doing 0.8 h up, or 2 h up, or 20 h downwind, or 5 h upwind, right? H is now our new measure. And the reason why we can get away with this is that by and large, obstacles produce effects on the atmosphere that scale. A small obstacle produces a small impact on the wind. A large obstacle affects the wind in a similar way, but just on a bigger scale. So if we use the height of the obstacle itself as like our yardstick, we have scaled the problem in a very nifty and useful way. Now, again, we run into your author has a background in this professionally before he wrote these books, and he has mentioned all kinds of really exotic equations and cite papers and so on that are about the techniques that were used when he was in the field, but all those will be updated with different, better parameterizations and better equations and new research long before you would be in the field, or, you know, I mean, that's just the nature of when you name drop like that, right? So it's better to instead, let's just, rather than look at those equations, which weren't really all that illuminating in some ways, let's look at, like, for example, what a typical output of those equations look like. And the book gives us this interesting diagram that I scanned, and it might not be entirely clear what's going on here. First off, again, on both the x-axis and the y-axis, these are being measured not in meters or something like that, but in terms of h. So like our y-axis there goes up to 3h, so up to 3 times as tall as our building. And so our building is sort of like at the origin of this diagram here, and stuff is happening downwind. On this diagram, they're saying the wind is going from the left to the right, and we are watching something happening to the wind. Now, it's important to also notice that the scales are radically different. The y-axis only goes from 0 to 3h, whereas the x-axis extending downwind up to 50h. I originally had a slide in here where I compressed the scale, so you got a sense of what this actually looks like, but it was unreadable. There was no point in me putting it in there, which is probably, by the way, the same reason why the author didn't do that either. All right, so we can kind of see our building is at the origin of this axis. The winds are going from left to right, and something is happening. But what is happening? Those values that they're plotting on here are the fractional reduction of the wind. So like the contour there of 0.1 means that the wind is being reduced 10%. And the contour of 0.5 means the wind is being reduced by 50%. And you can see that as you get closer and closer to the actual structure, the reduction in the wind gets to be more and more. In fact, it probably gets all the way up to 1. In fact, maybe it even gets to, oh, don't even worry about it. The values near the axis itself are meaningless. The equation is not designed to figure out exactly what's going on, like in the immediate vicinity of the building versus, you know, several h downstream. You know, at closer than about 5h, this is not quite the ideal parameterization for such a thing. First off, notice that everywhere, excuse me, in this parameterization, the winds are decreased by the presence of the obstacle. Is that your experience? Probably not. If you go to Chicago and walk down Michigan Avenue, you become aware of why they refer to Chicago as the Windy City. As winds come in off the lake into Chicago, these big tall buildings down at street level, you can get incredibly strong winds. That's actually only part of the story as to why Chicago is called the Windy City, but whatever. Yes, in the immediate vicinity of a building, you know, right as you go around a corner of a building or something like that, there can be very strong winds, but the overall effect of the obstacle to the flow is definitely to reduce the speed of the wind. Yes, there might be small areas near like the corners of the building and so on where the wind is stronger, but that's not the normal averaged over the whole area around the building. Averaged over the whole area, there's no doubt about it. The winds have been reduced. Notice too that that effect is felt very far downstream. Certainly 30h downstream, you can still find significant impacts. I think as you get farther and farther downstream from the obstacle to the flow, it starts getting to be in the margin of error as to like, are you really, you know, measurement errors and stuff, are you actually seeing the effect of the building anymore? Notice that the effect extends upward as well. Not as much, but certainly 2 to 3 h above the height of the building or the trees or whatever, you are also reducing the speed of the wind. That business of reducing the speed of the wind, even many multiples of h downwind, is part of the strategy of how shelter belts were built, or sometimes referred to as windbreaks. These are those patches of trees that you see in lines like along the edge of fields or framing the edge of a farmyard or something like that out in the country. Those are out there to reduce the winds over an area. Here's a lovely example of some shelter belts. I grew up on a farm in Nebraska, and we certainly had shelter belts and windbreaks built around some of our fields and on the north and west sides of our farm yard so that it would reduce the speed of the wind. When you drive out in the country, you will often notice that there are these strips of trees between fields and so on. That's not just the farmer being too lazy to take the trees out or anything like that. Those were generally planted there, or at least the trees that were there first, and those trees have since fallen, but other trees have grown in, were planted there. In fact, in the 1930s, that was a big Civilian Conservation Corps, or CCC project, under part of the New Deal. They built, what was it called, Project Shelter Belt or Operation Shelter Belt or something like that, put in thousands and thousands of these kinds of shelter belts all around the United States, thinking that they were useful for reducing wind erosion of soils, which was important considering, they also had the Dust Bowl going on at that time. It's actually one of the bigger examples of geoengineering that we've ever tried deliberately as human beings. Why do people do that, by the way? Why do they have these shelter belts around? Well, the key reason why they typically are around modern farms and so on is because they reduce the need for heating and cooling. Both heat loss in the winter and the loss of cold air inside of the building in the summer are related to the rate at which wind is flowing over the building or around the buildings or whatever. So if you can reduce the rate of wind on your farmyard, you can reduce the rate of heat loss in the winter and the rate of cold air loss in the summer, and reduce your expenses associated with heating and cooling. The original strategy, as I mentioned, for putting in those shelter belts back in the 30s was to control soil erosion by the wind. A lot of them nowadays also are maintained as part of our management of drifting snow strategy. This is not the context to get into this, and I'm not the right guy to try to explain all the details of how they place shelter belts in various distances away from roads to reduce the chances that big snow drifts. They want the snow drifts to form, but they don't want them to be on the road. Though by slowing the wind down the right distance away from the road, the wind deposits the snow in drifts harmlessly in the ditch rather than across the road. There's also, of course, a role with them with regard to things like habitat for wildlife. There's a role for them with regard to privacy and noise abatement on busy roads and so on. But they really do have this wind application as well, which of course means obviously you have to be aware about things like that when these kind of obstacles that are in the environment when you are trying to plan a wind farm. It gets even more complicated. Of course it gets even more complicated. That's what seems to be the theme in this class. That ought to be the name of this class, wind energy. It gets more complicated. Because a lot of these objects have some porosity to them, as in they are somewhat porous. We've been treating all these obstacles like they are solid and unchanging, but that's in fact not in general the case. Like a shelter belt of trees, for example, clearly has an annual cycle to the extent to which flow can penetrate through it. In the winter, when the leaves are off of the trees, assuming they're deciduous trees, clearly flow can penetrate through the shelter belt much more readily than it can in the summer when it is heavily laden with leaves. Does that mean somebody has to actually study that and know that? That seems to be the other theme for this class. Somebody has to study it and figure it out and make it work for your site where you're trying to build this wind farm. Now, when you think about changes in porosity and of a surface and so on, the classic example is shelter belts. Atmospheric science majors always learn about that and so on as being an example of how, over the course of the year there can be this change in porosity. But porosity is actually an interesting concept in architecture too. Sometimes you think you've seen the weirdest damn thing you've seen all day, and then you see one more thing. In the course of doing some YouTube searching for this, I found these videos about designs of architecture where they are open to letting flow go through the building. There are actually vents and channels designed in the building to take wind from the outside through the building. Now, I mean, there's actually a porosity to this structure. Apparently structures like this, at least all the architectural firms that I found online that had examples of this, were all in Southeast Asia. And their sites were advertising it as being a cooling issue. That by bringing fresh, cooler air through the structure of the building, through hallways and so on, it kept the air fresher and cooler and so on. And that may very well be, I don't know. But you don't see this in the United States very much, where these buildings have a certain porosity to them. Okay, obstacles to the flow. Keeping that straight from roughness turns out to be important, both in this module and somewhat to extent later in the course as well. Let's actually take advantage of this time here at the end of our lecture to have a few quick questions. Question 1. The net effect of a major obstacle to the flow, like a building or whatever, is to blank the flow, strengthen it or weaken it. Okay, make a choice from those two options and get a little feedback before you move on to question 2.